Well, hi there. Welcome to the Broadcaster's Desktop Resource video series, our lunch gatherings on Thursdays. I'd like to invite you, if this is the first time you've seen one of our videos, to hit the little subscribe button, and then a little bell next to it will let you know when we post new videos each week. This week, Nortel, I'm happy to say, is our proud sponsor. They want us to know and to share with you their special deal right now about a second exciter when you buy some of the GV series transmitters, and that is really a good deal. At this point, I am really pleased to have Sean Edwards and Kyle back, Kyle Sanders, and we're going to talk about FM propagation. And Sean, I'm going to just turn this thing over to you and have at it.
Thank you. So last October we did a luncheon with you, and we talked about patterns and HFSS electromagnetic simulation software that we use, and how we're utilizing that, and then segued into how the patterns are actually measured. And that we introduced, we had Bob Surratt with us during that session, and he's absent from this one, but Kyle Sanders, whom we introduced for the first time last October, is joining us again, and will be giving the bulk of the presentation. And we're also joined by Chris Taquino, who is a recent addition to our RF engineering group here, and was involved in the making of the video and the work that Kyle did for this. So on that note, I'd like to start with just a little introduction, or a little refresher of where what we talked about in October, and we'll segue into how that actually gets done with some narrative from Kyle. So now, if I want to present here, I need to share the screen, and I need to share this screen. Share at the bottom corner. Share at the bottom. Now, can I get it started?
There you are.
Yeah. And I can get it started from the current slide. All right. So then we were talking about how it all starts with the dipole, but when we're talking about isotropic radiators, that's where it really starts, with the spherical radiation of an idyllic radiator. And then our dipole is, so if you reference to the isotropic radiator, you're going to have the one value reference to that, so dBi. Or if you're reference to, for gain in the dipole, it's going to be dVd, which is 2.14 or 15, depending on who you talk with, higher than the isotropic. So just starting a little background here, and let's see if I can advance this. And we talked about how the fields form, the electric field there, and magnetic field, electric field on the end of the arms, and magnetic field around the feed point, and how that produces the idyllic donut pattern, vertically polarized in this case. And then we moved on to show the slices of the azimuth pattern and the slice of the elevation pattern. We talked a little bit about axial ratios and polarization ellipses. So if you have circularly polarized, you have a time variant between the vertical and the horizontally polarized energy, so that you get a rotating circularly polarized field. And then there's the axial ratio of the polarization ellipse. So how much of the horizontal and vertical do you have in proportion? And then we talked a little bit about how that is defined for the electric field in those cases. So again, this is just a review, so I'm going to skip through some things here. If there's any questions about this later on, I'd be glad to answer those for you. And then we looked about circularly polarized antennas. in this case, there's a panel with two sets of dipoles, the horizontally polarized dipoles and the vertically polarized dipoles, and how when they're fed properly, create a circular pattern. And here's the back side of the panel, the currents flowing on the panel. As you can see that that's a rotating field. And how is that realized in a side mount? Well, this is the simplest version of a side mount that I can think of for circular polarization. And it's used to be called a cycloid. It's a ring stub. And you have the horizontal, it's basically a dipole laid on the horizontal plane and folded around itself, some of it occupying the horizontal plane, some of it occupying the vertical plane. And there's a time variant between when each portion of that radiator is excited, so you get that time variant that you're looking for circular polarization, and you get the excitation in both polarities. So in the field looks more like this. So that's the magnetic, and that's the electric at the end of the arms, magnetic around the feed point, just like in a dipole. But now you're exciting both planes of the horizontal and vertical plane. And this is your azimuth slice of it. So you can see that you have two components now, and it's in a rotating field. You can have two components if there's no time variant between the vertical and horizontally polarized energy, then it's slant polarized. And so in this situation here, this example, we go on to the next sort of complexity of a side mount, circularly polarized, which is kind of like two of these sharing the same ground plane here. So you can imagine what the arms are now bent a little bit to the vertical arms are oriented a little bit off of vertical. And that is because the vectoring that occurs between the two fields, if they were straight up and down, you would have a predominantly vertically polarized CP, where you want them to be equal, ideally. So by leaning them over in the vertical plane, we reduce that vertical, and the HV ratio is restored. But this is showing, again, the vertically polarized and horizontally polarized energy, which yields a pattern that has two polarized fields occupying the same volume in free space. And that would be the azimuth slice. So we're going to talk about now how that gets done in pattern analysis, how we take these rudimentary models and predict what's going to happen in the far field when they're placed on a specific tower at different types of configurations. And that's where Kyle comes in, where he specializes, and I'll hand it over to you, Kyle. So you want to stop sharing that, right? And then you share.
Alrighty, my name is Kyle Sanders. I'm mostly the pattern guy here, even though we wear a lot of hats around here, production, testing and tuning and everything else. And we also make feature videos, really cool ones. Okay. Like I said, back in October, we were with you guys. I gave an overview of our pattern range, just kind of dip our toes in. I'd like to explore and share with you some of the basic process and understanding of how we come up with some of these final patterns. So for the example, we'll be using a model of the SLV. We started off with a randomly chosen 24-inch face Pyrod tower, randomly chosen because it's only 5.3 inches at scale. The scale we use is 1 to 4.5, so the 12-foot self-supporting tower is still pretty hefty in my opinion. The typical mounting solution for the SLV is a vertical offset pole. From this point on, every decision made in the mounting process will affect the pattern. There we go, we got the pole on. Now we take our pint-sized antenna and tune it, preparing it for a free space measurement. Free spacing is to check our model and the range. We will replace it with a log periodic radiator that we use to set elevation parameters. I can control it. And what we want to pay attention to is the H&V ratio, the horizontal and vertical energy, or the RMS of those two polarities. And we also want to notice the overall shape of the pattern. What we would like to see is a close match of that H&V ratio and a near isotropic azimuth. It won't be perfect. As you can see, it's sitting on a metal pole, and there's speed line, there's polarity losses, and we do this in every sort of weather you can imagine. But it has to be comparable with the range precedents. There I am trying to bore sight it. If it's off, the VNA will tell us. If we have any questions at all about the range, even today, HFSS can tell us and put our mind at ease. Taking anything metal I brought up there with me, any tools at all, because that'll affect it. And then here's the actual software going to work. So on the right, there's the increments of it turning, and on the left, there's the actual program itself. So right here, it's at a quadruple speed, 4x speed, so you can imagine how slow that is. Downrange is the receiving dish. It's taking phase and amplitude measurements at every 5-degree increments. And right there, we have our free space. So it looks pretty good. We got a nice little ball rating around the pole in the horizontal plane. And then the vertical is slightly pushed forward thanks to the pole that we mounted onto. After we've determined that the model and range are trustworthy, we proceed to mount the antenna to our tower. It is for sure going to be placed on the before mentioned vertical offset pole, but we could choose whether that pole gets mounted on a leg or a tower face. That choice hinges on the tower real estate, orientation, and customer preference. After those, if I still have that option, it comes down to whatever's best for the pattern. I'm keeping in mind a minimum distance for hardware clearance and a maximum distance to adhere to weight and wind loading restrictions. Special attention is paid to that dimension thanks to the reruns I had to do after engineering deeming my mounting solutions as impossible. So I become a better mechanical engineer with every pattern. I get some leeway in choice and expression on how I go about the patterns, but often reality slaps me down and restriction becomes something to overcome. Anyway, here you can see the influence that the tower places on the radiator. The vertical is mostly untouched in the front because it is already being pushed forward. The front to back ratio is more pronounced though. The horizontal front is slightly pushed forward, but it is still radiating around the tower. Right now, the bay is 1.75 inches off the tower leg, or a little less than 8 inches at full scale. So it's pretty close to our tower still. What we want to see is what it looks like once we pull that bay away from the tower. Got some help from my beautiful assistant. Oh, that was me. Sorry. So as you can see us, we're squinting at it with our measuring tapes. Once we get closer to a final destination, we bust out the calipers and squint extra hard at it. All the patterns leading up to this point are almost roughened, even though they are still strict measurements that get logged so that we can follow the trends. Looks like the biggest tower climber I've ever seen. He's tightening everything up. He's pulling that feline taunt, making sure there's nothing in the aperture. Yep, everything looks good. She's saying a little hike back.
Yeah, I have to interject. For every iteration, there's that trip up and down the stairs, which explains their extreme good physical condition. And you can see I don't make that trip as much anymore. So
Cardio in. At 4.5 inches off the leg, the vertical grows a little bit, and our H&V ratio is basically right on. Depending on the DA that is allowed, tower effects can work with you. Sometimes the antenna just wants to be away from the tower. One way you can mitigate the influence of the tower is to use parasitics. Through the use of parasitics, you can create a sort of a buffer between the antenna and the tower. It's kind of like modeling your own tower behind the antenna. Horizontally situated paras form the horizontal energy, and the vertically placed parasitics manipulates the vertical energy. The shaping function of the parasitics is kind of like a push and pull fashion. So the design of the SLB and some other antennas like the 6815 are different from our ring and stub design. So they need a different type of parasitic. That type is essentially a horizontal para that's been bent to a certain amount of degrees. The placement is normally a quarter wave above and below the bay. I say typically and normally in this case because parasitics can take on a ton of different configurations, especially with the more crazy DAs and the more desperate I get with the study. I do normally around 20 pattern spins for a normal one, but I've done 100 or more in a few. Okay, so here we're looking at the effect of the paras. We have a nice little mushroom shape that the horizontal decided to take on. There's some radiation still left out the back of the tower. Both polarities are almost uniformly pushed forward and cover each other pretty well. To match those RMS values of the H and the V, I might choose a different length of parasitic or move them closer, further away from the bay. What I want to do now is do some focusing. So there was a very wide half power beam width from that last one and a bit of backward radiation that I'll try to get rid of for demonstration purpose. What I'll do to accomplish this is flip the paras forward. This is for extreme DAs and something that needs a lot of focus. I don't do it a lot, but it's a neat trick if you need to shrink your pattern down to fit inside of something. It's a little windy. You can see the nice main panoramic or spooky woods. I like to walk around at break. It used to come out like 20, 25 feet or something. And we weren't sure if it was messing with the pattern, so we moved it all back. It's a good thing about the pattern range. We could check whatever detail we want. Right there's the tuning rack. It's where we tune all your antennas. It's a good thing about being in a small town is with all this testing and operating, we get a lot of isolation from any noise from anywhere, so helps out a lot. Passing over the shop to my second home, back to the receiving dish. Bless you. Okay, here's what happened. So you can tell that half power beam width got sandwiched up really tight. There's sort of a disparity between the H and the V now. So if this certain pattern came close to fitting in whatever DA I had, I'd probably work with the H and the V ratios. Do that by pulling or pushing the bay further away from the tower or closer. We're already 4.5 inches out, so I might mess with the parasitics there a little more. As far as pattern goes, every tower is different, every frequency, every bay. With so many variables, it's hard to tell what any tower and antenna model pairing will behave like. And the room to interpolate anything is very small. So at times it feels more like a craft or an art form rather than anything scientific. There's a little math at the beginning that helps me give me direction or a path to go down, but after that, it's more or less just feeling your way through it. But at the same time, there is still an amount of predictability. With tools like HFSS and people around me who have decades of experience, the process can be shortened, demystified, checked, and explained. It's all about noticing the pattern. I thank you guys. I hope you enjoyed it. Okay.
All right, and I'll continue on a little bit with so I want to talk a little bit more about, so you've seen through Kyle and Chris's work, the work that goes into the process of spinning a pattern in our range, where scale models of the tower, scale models of the antennas, and scale models of every other component. And the more accurate those models are, the more accurate the result is going to be. So that's where that communication between our customer and what their desire is, and our technicians, that communication, the detail about what's on the tower, how the tower is oriented, and where the population base is, where you're wishing to cover the most, because you might have an envelope, but some areas of that envelope are going to be much more important to you than others. And that's the kind of communication that helps us tailor a pattern specific to your needs. But talking a little bit more about HFSS is, right now we're in a period of correlation, collaboration, and I believe that there's a petition in front of the FCC at this moment for rule making changes to accept calculated patterns rather than just measured patterns in FM. That's done in television, but not yet in FM. So that's the way of the future. I think that if you look at the results from HFSS compared to the results of the measurements, it really depends on the accuracy of either model, which one is more accurate, which one is going to be more what you see in the real world. The great thing about having both tools is building that correlation between one and the other. And that's actually what we're in the process of doing right now, educating Kyle and Chris on the use of HFSS for pattern work, not just for design work, but for pattern work. And an example of how that might work is, if I can find this file. I've had it. So we looked at, and I'm not sharing this, am I? I'm gonna get this. Let me try to get back here and share this screen here. And start it. So we talked about how the SLV was in free space. You can't get this sweep on a range. There's got to be a connecting wire. Unless you have a wireless system, we don't, and can't see that in the foreseeable future. But you have to have a connecting wire, which is essentially a vertical reflector. So what we're seeing here, the closest that Kyle can get in the range for a free space, truly free space pattern, is what he showed you with a slight push to the vertical. So once you put a pole on that, it does that. And you can see the comparison, if you remember the plot that Kyle just showed you of an SLV on a pole, is essentially this pattern. There are two different sweep frequencies, so there's slight differences. But we are in the process of sweeping and measuring an antenna and proving that the HFSS twin of it. And through that process, we verify the range and verify HFSS and position ourselves for that eventuality of having computed patterns accepted. And some advantages to doing that. In the measurement world, there's always going to be, in the real world, there's environmental conditions that we have to overcome. There's days that are just too windy or rainy to work. There's range maintenance that occurs, and in the virtual environment, the worst thing that can happen, and absolutely the worst thing that can happen, is the crash of your system. So I just wanted to go through a little bit of this idea of placement on a tower in HFSS and sort of mirror what he talked about. So in this situation, you have a free space SLV on a pole, it yields this pattern, and then mounting it on a tower structure on the leg, you get something like that, which is not bad, but could be optimized perhaps. Distance off the tower leg can push these nulls in or pull them back out, so it's more coverage in these areas. And then the introduction of the parasitics, as you saw with the actual measured patterns, can produce patterns like this. But there's one particular I wanted to show, is this arrangement. It's on a fairly large tower, and you would think that the antenna should be a ways away from it, where that's the pattern that's produced from that arrangement right there. And when we pull the antenna right next to the tower, that's when we actually get the best pattern. So this goes in hand with what Kyle was saying about, you know, predictable and intuition goes out the window because of so many variables. And it's through this optimization on the pattern range and now being mirrored with HFSS that the patterns are realized. So let's see. There's something else I wanted to touch on here. This is a review of last year's. These are slides from last year's presentation. So here you see that range, but also a nice white stuff on the ground when we did these videos, these photographs. So at this point, I guess if anybody has any questions about what we've covered so far, it's a good time to talk about it.
Well, I think we're going to have a lot of questions, Sean. I'll start with one that many will have in their back of their mind. I spoke with Bob about this years ago. You're doing a miniature. You're doing a 1.45 to 1.
Yeah, 1.45 to 1. Yes, 4.5 to 1. Excuse me. 4.5
to 1. Compare that with full size ranges. Some people say if you don't do it at full size, it's no good.
Well, I think we've proven that over the 50 years in business doing this, that's not necessarily the case. What I think can happen, and what people may be referring to there, is again, accuracy of when you spin a pattern on a tower that you've built with an antenna that you've designed in a construction, the feed system that you've designed. There are absolutely no questions about what's in the tower. You've covered that. So when that stresses the importance of getting the correct information for the model. If the model is accurate, then the results will also be accurate. And we take steps in the process to ensure that happens, from annual maintenance of the range to periodic measurements compared to a baseline, to daily calibrations, and attention to detail on documenting those dimensions and whatnot. So in the beginning of the process with our contact with the customer, we send a tower information sheet, and it has a series of questions on it that, I wonder if I can find that. Do we have that somewhere, our information sheet?
Let's back up just a half a step, Sean.
Yeah, sure. Yeah.
And before you added the parasitics, theoretically, it's, at least as the FCC considers it, a non-directional antenna.
Mm-hmm.
How many people come to you and mount their non-directional antenna to know where the bulge is?
That we termed, and that's one of those areas that everybody has to be very careful with. There's optimization is acceptable to a certain degree. You cannot you cannot put an antenna on a tower through optimization and have, I think it's more than 3 dB of gain. So you can't, this was something that was discussed at length through a situation in a certain part of the country where there was a non-directional antenna mounted to the face of a tower, and it had like 2, almost 3 dB of gain or more. Actually, it was 2 or 3 for power gain, so more in dB. And there was interference issues. And through the process, I think that the ruling, and I don't recall the actual ruling, but from my understanding, it was proven that the antenna was intentionally optimized, even though it didn't have parasitic elements. The tower itself gave it gain, and it became a directional antenna. Under the intent of the law, it was, or intent of the rules, it was no longer an omni antenna. So if you don't have any study done and you put an antenna arbitrarily on a tower, you don't know what the pattern is until somebody calls and says you have an interference. In that situation, it's a little different. There was no clear intent you were trying to optimize the antenna for gain. It just happened. In that situation, it would be addressed probably by a complaint if there was one. But I think that it comes down to that intent and as to what's acceptable or not. And ultimately, if it's challenged, what you actually have for a pattern off your tower. Does that address your question, Barry?
I think that answers most of that, and I'll toss it up to other folks here. I don't know, have you watched the chat there, or shall we read some of their comments?
Have not been catching the chat. Let's see.
Chat.
What is it?
Chat.
Chat. There it is. Okay. So we have is the radial scale dB. That's in relative field. That was from Chris Hayes to everyone. What about interference reflection measurements? That's from David Stewart. Interference reflection measurements. I'm going to ask you to clarify that, David. Dan Ellendorf had to leave. Sorry to see you go.
Yeah. One of the manufacturers does a fairly short range, and they refer to them as reflection interference modeling. They'll take the transmit signal, the reflect signal, and I don't know what math they do to this, what post-processing they do, but the number they come back with is, they call it a reflection interference or interference reflection test range.
So like ground bounce?
Yeah.
Okay.
Yeah, that's actually something that's been measured on our range and adjusted for acceptable levels. And the ranges, outdoor ranges have a noise floor too, where something like HFSS doesn't. So you end up with a noise minimum, and you can only measure, I think ours is 40 dB, so, which is really good. But if we were to try to do a front to back ratio of 50 dB, we couldn't do it on this range. So I'm not sure who could, but
Well, so that's like when you're looking at just the return loss or the VSWR. 20 down is pretty good. 30, gee, that's nice. And at 40, you're tapping on the instrument to see if you really believe it, because you really do get diminishing returns pretty quickly.
yeah, and that's the same case with the range. It's similar to that with the reflection, the reflection coefficient for an instrument. That's a good analogy. I have a question from Harold Halakainen. What is the correlation between the computer model and the scale model, plus or minus a dB, or what? And yeah, it's in that or less, depending on the accuracy. Again, the models have to be identical. And that comes to back to that point of that very important part of the process between the customer and and us, is that complete tower details, and including coax, ladders, appurtenances above and below the antenna that are within a wavelength. All of those things matter. Recently, we did a pattern that was on a Valmont antenna sandwiched between two halos, and we found that it had very little effect on the main lobe, but what was the differences between having those halos there and not having them there was maybe a 5% difference. But what we learned through the process is it was the side lobes that were interfering with the, that were being reflected back. And by changing the position on the tower, we were able to minimize that. So, you know, that's something that we couldn't have done in our field measurements. And I still have another question. Where's the correlation between scale measurements and final installation measurements? Those measurements on the final model are taken and scaled back up to full scale by our mechanical designers. And so that information is all recorded at scale values on the pattern. As you see on this in the presentation, the slide that you're looking at, there's parasitic length, which is noted as 12 inches. That's actually scaled value. So that, and the C dimension is the distance above and below the radiator from center line. That's the scale value. So those values are transformed back into scale, and the actual production models built from those values.
Grady?
There's one more question I'll address here before we take any more is has anyone provided drone after built measurements of the full scale and compared it to what you expected from the model? And that's a really timely question, Tim, because drone measurements have really taken off, so to speak, and are starting to be utilized in more and more places. They've had their own restrictions and flight plans that they've had to work around, and measurement errors. And I think we've seen a presentation recently where they looked at, because they couldn't measure the far field because of the amount of elements in the array, far field was so far out as beyond the flight plan. And they had to extrapolate, they had to measure near field with the drone. And it matched to predicted near field from HFSS. And there was a way to prove that the far field was doing what it was supposed to do. So, and this is another manufacturer, this was a television presentation that I watched. And, you know, we're using the same tools and the same methods of correlation, and it's really become a powerful tool to be able to look at things that you never really could look at. And now that we're measuring with drones, we're able to look at that aspect that the drone is actually capable of measuring and still make predictions through interpolation, extrapolation. Is there any other questions?
I've spent a lot of time. Can y'all hear me?
Yes, sir.
I've spent a lot of time over the years up at the Shively range. Always enjoyed myself a lot and paid attention to what I saw them doing. However, over the years, I've also worked with consultants with antenna systems manufactured by other manufacturers for clients of mine. And one of the things that I've run into is a consultant. This particular one shall be unnamed, and it was 15 years ago, 20 years ago. They will purposefully mount the antenna on the tower so that they will get either the horizontal or the vertical to go exactly where they want it to go as a directional. And then they will put parasitics on the tower to get the opposite polarity to basically sit on top of the problem that they have, and then tell the FCC that this is the best we could do. And the FCC has accepted it. I was blown away, but I observed that only one time, but it was a well-known, very active, and a very successful consultant at the time. Another thing, say again?
No, I was just agreeing, yes.
Another thing that I noticed, however, up at Shively, I don't know if they do it this way now, but most of the time, or maybe all the time that I've been up there, they actually use the distant antenna to transmit, and they receive with the antenna under test. And the entire antenna range is designed to minimize environmental effects on what the antenna under test receives by the way that it's built. So when they're rotating that antenna, it's getting a constant signal from the stimulus. And that's one of the ways that they have always, in the years when I used to go up there, which hasn't been lately, unfortunately, they were able to minimize environmental impacts at the range.
Yeah, I can see why that could have advantages, because it really depends now on the beam width, because they're reciprocal devices, the beam width of the transmit, or what should be the receive antenna. I think that what you're referring to is probably trying to illuminate the model antenna, the actual, what's going to be the radiator, with a pencil beam. Oh, sorry, gentlemen. A pencil beam, sort of a narrow beam width source, so that there's fewer reflections there. And that's an interesting, that's not how we do it today. We've through gating techniques and through absorption techniques and the collimation of the receive and transmit antennas and daily calibrations to a known value, which is the log periodic at 45 degrees, where the peaks are equal. Through those processes, now that's how we assure that the range is calibrated and free of environmentals.
Well, my one final comment before I go away, and thanks for your patience. A couple of times back in the late 80s, early to mid 90s, I had customers who actually, after antennas were tested on the range, built and installed, hired a helicopter to fly the pattern, and we actually had to get FAA approval of our arrangement of horizontal and vertical elements on the helicopter, on the aircraft, and we flew the patterns. And I must say, we were really happy with how well the prediction of the test range matched the real environment. I'm done.
Oh, thank you for that. And that's a nice testament. But exactly what I meant earlier, through time-tested experimentation, through time-tested sales and support, and actually implementing these things, we find the same thing is true, that scale model testing, it done well and done accurately, is as good as full scale, at least at FM. Thank you for that. That was it's always nice to hear positive things. So any other questions? Yes.
Sure.
Yeah.
Sean, I would also like to echo Harold's comment. I don't know that you addressed it. It was saying on a scaled model, you're operating the 400 megahertz or so range. How much power? Is it under the Part 15 limits? And do you have an experimental license? My other question is, does operating in that range actually provide more accurate results due to lower RFI than operating on the actual FM band? I know the FM spectrum is not especially congested in Bridgeton, though I do serve there. So do you have any answers for that?
Yes, I don't recall off the top of my head what the power level is, but I do know that it was that was one of the considerations during the construct of because the antenna range was revamped in 2011, I think. And our engineers at the time, Bob Surratt and Martin Gregory, Peter Long, did that design. And I know that adherence to Part 15 was consideration, because we looked at the specifications of the transmitter that was selected for that. We also measured the gain characteristics of it. And I remember that being part of it, although I don't have any specific answer of what the power range is. Do you know what that is?
I looked at the amp. Yeah, it's less than 10 watts for sure.
Yeah, so
If
it's a
that
couple of
helps.
watts and
the 400 megahertz range, I've never noticed anything wacky like
Yeah.
we do testing tuning
yeah.
on the rack. So yeah, in that FM band, we get some noise here and there. We just have to kind of wait it out or maybe tune it another day. But yeah, nothing on that band, so it stays pretty quiet and it's very reliable.
I did have another. Yeah, I did have another quick question, and that is when you're doing a scale model, 4.5 smaller, how do you deal with getting hardware? I mean, your standard antennas use like 1/4 inch 20 or 5/16 hardware, but 4/5 size of that is not exactly an off-the-shelf item.
That's right. And at some point, what we learn is through experimentation during the initial stages of all this, and through work in HFSS, I've directly learned about these things, is that there are some things that are too small to worry about. They don't make a significant difference. And it comes down to portions of wavelengths and where these appurtenances are that may not be exactly modeled for. So when you're talking about connecting hardware, as long as it's not protruding, say you had a bolt protruding 8 or 12 inches from something, that you would want to model like a foot peg on a climbing peg. You'd want to put that in the model. But something like a bolt head that's protruding only an inch or so compared to a wavelength of 10 feet is insignificant. Unless the whole pole had bolts all over it and the actual diameter had increased by an inch, then you might want to model that. But in general, those kind of things, the hardware, we use the things that are closest as we can. And when it comes down, so if you can, am I still sharing this photograph here of the model antennas?
Yes.
Yeah, you can see here, I think, on the bottom, hanging over the frost wall there, you see some log periodic antennas. What's important here is the dimension of the boom, the size, the diameter of each element. The diameter is very important. The location, relative location to each other, and the overall length. That needs to be scaled very, very accurately. When it comes to feed point particulars, we feed in the same point down here at the bottom. I don't know if you can see my cursor or not, but we feed at the same point on the log periodic, but it's not exactly the same feed design. So those sorts of things are insignificant when it comes to the radiated pattern. What's more important is the radiator surfaces themselves.
I got a question about range configuration for a minute. By the way, my day job, we do satellite antennas, and we have a big range, and we have the AMTA. You're welcome to come down there if you get a chance. Antenna Measurement Techniques Association. It's going to be in Daytona Beach this October. Great organization, and you guys would fit right in. Y'all would really enjoy it, I guess. But there's basically two types of antenna ranges. You got elevated range and ground reflection range. And the problem is, at these frequencies especially, trying to keep the ground contamination from entering the vertical quiet zone. It's probably not as big of a deal if you've only got a single element. When you start to get in an array, I don't know if you ever do a field probe where you've got to have a uniform amplitude illumination from your light periodic source antenna. You've got to keep that fairly uniform, or it very much will contaminate the measurement. I would be much more concerned about that than the scale factor that some people have been talking about. But especially even at UHF frequencies, the criteria for an elevated range is to keep the main beam of the source antenna off of the reflecting surface, and that's really hard to do at UHF. You can get a ground reflection range, and maybe that's what you're doing. I couldn't tell from your photographs. It looked like an elevated range. And then what you do is you adjust the height of the source antenna so that the reflected signal and the main beam are in phase alignment with each other. It kind of contaminates CP if you're trying to get CP measurements. That's another issue. There's a couple of other things you can do. You can use diffraction fences and longitudinal wrap, things like that, to try and reflect the ground reflections away. But that looks like a big concern. What about ground reflections? What kind of vertical quiet zone performance do you get? Because especially if you get like a 2-element array, that's going to be that's a big deal. Like that's much more of a contamination and a measurement error source than I think anything else. But anyway, I'd be interested to hear what you're saying about that. So
that's a great question, Ray. And so essentially, all of those things that you talked about have been used here in the early stages of the development of the range. First, it is elevated, and secondly, the ground bounce has, that's part of the design criteria, is to reduce that to a point where it's, it's not contaminating that vertical polarity. So there's, in addition to diffraction fences and absorption materials on the ground and changing the height of that source antenna so that those are all sort of, each one of those solutions is a way to mitigate it, but each one has its shortcomings, pros and cons. And what we found works very well is blocking that at the receive antenna with absorber material, or changing the focal the beam width of the receive antenna. Those are two techniques that we use to keep that contamination from happening. And we don't do that's another limitation of our range, is we do single element azimuth patterns. Very rarely you're going to see more than one element in the vertical plane. So that is what we're doing, is creating the unit pattern that you would use in array multiplication. So when you look at that, the azimuth pattern essentially stays unchanged. Interpolating the elevation pattern from the unit pattern. Does that answer your question?
It's Hollis, Lyon, and Clayton. Actually, my company put it out. They were my proteges from a long time ago. It's kind of like, we call it the Blue Book, the Antenna Measurement Handbook. Look in chapter 14, and it gives the range parameters for both an elevated range and a ground reflected range. And I actually have it on a spreadsheet. And before anybody goes up on the range, they have to, pretty much comply with each one of these. Anyways, it's in chapter 14. It's the last page, and it's kind of a checklist. We kind of use that, but I don't know if you have that. It's Hollis, Lyon, and Clayton, and they used to work. They're all deceased now, unfortunately. But they were kind of.
What was that text?
Well, it's from Scientific Atlanta and Antenna Measurements Handbook. A lot of people call it the Blue Book. Hollis, Lyon, and Clayton. Great book. I mean, it's our Bible. We call it the Bible. And in chapter 14, we have a checklist for both an elevated range and one for a ground reflection range. And before we send anybody up to the range, I have a spreadsheet. I make them, show me that they're kind of meeting this, because that's a good thing. I think somebody alluded to a lot of times that if you're not really careful, and antenna measurements are very difficult, you get data collection and not real antenna measurements. And we actually have something called a field probe that we use. It actually is it's like an I-beam with a motorized carriage on it, and it takes a probe up and down, and we can actually sample the vertical and the horizontal field. You want to try to get it within a half a dB or something like that, if you can. I know sometimes it's kind of a compromise, especially at this frequency. But there's art to it. We got folks, that's all they do is antenna measurements. So it's kind of fascinating.
It sounds certainly.
Maybe you can come down to the AMTA symposium. It's down in Daytona Beach, October 24th, I think it is.
Well, you're talking to somebody from Maine, Ray. Daytona in October sounds
good.
Great.
I like Maine in October too. We used to go up to Maine and like a picture postcard around early October.
Right. Yeah.
October. Love it up there. Great presentation, guys.
Well, thanks for your question, Ray.
Anyone else want to join the conversation? Harold?
No, I thought the ground reflection thing was interesting. And of course, you could put RF absorbing material on the ground. In the chat, I said plant RF absorbing grass, but that would help eliminate that. I've most recently worked for a company that also manufactured loudspeakers, and there's the half plane measurements there where the speaker is sitting on the floor versus being elevated. So it's a very similar thing.
Yep, it is. It's interesting you mentioned RF absorbing grass. We actually did that at one point in the past, planted shrubbery down between the range, the transmit side and the receive side. Gating, using electronically removing that ground bounce is also possible. So what you end up with is usually a series of tools that you use to your advantage to reduce that.
Yeah, in loudspeaker stuff, they do impulse response, and so they reject everything after the initial arriving signal, so the reflections are not included.
Yeah, that's a great technique as well. I can't think of how we might implement that, but
it gets tricky when it's the reflecting surface is close because everything arrives near about the same time.
Right. Yeah. Anything else? Any other questions?
This is great. Thank you.
Yes, thank you.
Well, Sean, do you have a screen there with your contact information on it that you'd like to flash up?
Maybe. No. Yeah, we got a website, but no, I don't actually. You know what, Barry, you caught me off guard. I didn't produce that. But you can reach either one of us at 1-800-744-1888, 744-8359, and ask for Kyle, Sean, or Chris Taquino. And hey, Grady, how you doing? I see your face popped up there. I don't know if you can hear us.
Hello?
Hi, Grady. I just saw your face popped up there.
Oh, well, I was talking earlier.
Oh, I was speaking to you.
Yeah, I was one of the early people that kind of threw some stuff in there that may or may not be useful. At my age, and after all the years that I've been in this business, as far as I can figure out, they've invented something that completely replaces the stuff that I understand. And I'm lucky to get any money out of the industry now. Yeah, I know. It's sometimes moves fast. That's what we're trying to do here is with HFSS and trying to prepare for the eventuality that they'll actually accept these calculated patterns. I figure when the checks stop coming, I have in fact reached the end of my usefulness. So again, that's anybody that wants to reach us, it's www.shively.com, 1-888-744-8359, and ask for Sean or Kyle or Chris.
What's the Twix number?
Hey, thank you. Who did that for us? That's great. So that's how you get in touch with us. Whoever did that, thank you very much.
You're still
All right, I think that's it for us, Barry.
Well, Sean, thank you ever so much. We appreciate this, and nicely put together. I really enjoyed that video, and I'm sure others will do so as well. And want to invite you back again to talk more FM antennas and another topic, another time. Yeah, be glad to. We could offer something on filtering too, if that's ever a question or something of topic of interest. So thank you for the opportunity, Barry. Appreciate it. Absolutely. As more and more stations co-locate, filtering becomes more important. And I've seen stations where there's 6, 8, 9 filters in a row, and they wonder why they have issues. Yeah, that's a complex system for sure. So we thank you very much.
I like that ringtone. Takes me back. Thanks, Barry.
All right. See you soon, I hope.
All right, take care. Bye,
now.
everyone. Thank you.
Right.